Welcome back. One of the applications that uses some of the circuits that we've been studying is that of a power supply. And a power supply is a circuit that converts an AC signal into a DC signal. So basically you go from a time-varying signal, typically with voltages of two polarities, to a constant DC voltage of a single polarity and hopefully a stable DC signal. The application for such a circuit is that, in most electronic circuits that we have studied, they require a DC source of power. If you think about your op-amps in your circuits, they're powered from either two DC supplies or sometimes a single DC supply. And this power can be provided via a battery, but the battery gets spent and eventually will need to be replaced or recharged. And so the most available source of power that we have to power up our circuits is that comes from the outlet. But the power that comes from the outlet comes in the form of an AC voltage. And so the first step, or one of the portions of our electronic circuit, needs to be a power supply that's going to take that AC voltage and convert it into the DC voltage level required to power up the electronic circuits. And so I've drawn here the skeleton of a standard power supply with the different steps involved. You can see that the power supply gets connected at the input side to a regular outlet, which in the US is typically going to be a voltage between 110 and 120 volts, and that will be an RMS value, but it's an AC voltage at 60 hertz. The voltage goes through a transformer, in this case a step-down transformer, and the output of the transformer is still going to be an AC signal, an AC voltage, but it's simply going to be lower in value because the 120 volts typically higher than the standard voltages we need to power up our electronic circuits, which could be in the range of 15 volts, 12 volts, 10 volts, somewhere around that range. So the transformer is going to step it down to something that's closer to the final DC voltage that we need. Then it goes through a rectifier. So in this case, I have included a diode bridge rectifier. And you can see that it performs full wave rectification. So basically it lets through the positive portion of the signal and then it reverses or inverses the negative portion of the signal. So you end up with a full wave rectified signal. Then you run that signal through a filter, which is basically going to be smoothing out that full wave rectified signal. And the idea is that you will end up with a constant voltage. You can imagine this will be like a peak detector circuit. And so once you reach the first peak, you should just remain stable at the voltage, but you're always going to have some losses. Your capacitor is going to discharge when the input signal starts going down. And so hopefully if the capacitor is large enough, it will discharge slowly until the next cycle comes through and it will charge again and so forth. And so you will end up basically with a signal that has a little bit of ripple. It's what's known as a pulsating DC signal. And then you run that signal. The last stage of a power supply will be a regulator, a voltage regulator, whose job is to take that pulsating DC signal and turn it into a very stable and constant DC voltage signal, which ideally will be independent of changes in the input, meaning the signal that's coming, the pulsating DC waveform, as well as changes in loading conditions. So the job of that voltage regulator is going to be that of providing a very stable output voltage. So we can take a closer look at the different stages. So as we mentioned, the first stage is going to be the transformer stage. And the job of the transformer is going to be to either increase or decrease the voltage level. If it is increasing it, we'll refer to it as a step-up transformer. If it's decreasing it, we'll refer to it as a step-down transformer. Notice that prior to the transformer, we've included a switch. And typically, you need some means to turn on the circuit. And typically, there is a fuse. And that's just so that if there are any surges in current, you will avoid damaging all your electronic circuitry. The transformer equation is given by V1 times I1 is equal to V2 times I2. Essentially what that means is that the product of the voltage and current, or the power on the primary side of the transformer, must equal the power on the secondary side of the transformer, which implies that if the voltage is decreasing on the second side with respect to the primary side, then the current must be increasing to keep that product constant. So how much the voltage and current increase or decrease from the primary to the secondary side is determined by the turns ratio, the ratio of the number of turns on the primary side to the number of turns on the secondary side. And so the turns ratio is equal to N1 to N2, number of turns on the primary to number of turns on the secondary, which is also equal to V1 divided by V2. So the ratio of the voltages is equal to the turns ratio. And just to keep the power constant, then the ratio of the currents will be inversely proportional. So let's imagine, for example, that I want to transform my 120 volts, and typically these are given in RMS quantities, so even though we're saying volts, the RMS is implied, and we want to step this down to let's say 24 volts RMS. And so in that case, I know that my V1 to V2 is equal to 120 divided by 24, or 5 divided by 1, and therefore my turns ratio N1 over N2 is going to be equal to either 5, or sometimes it's expressed to as 5 to 1. And that means that if my current on the secondary side, I2, let's say, was equal to half an amp, then that implies that my current on the primary side will be 1/5 of that. So the voltage decreases, but the current must increase by the same amount. So if the current on the secondary is 0.5 amps, the current on the primary must be 1/5 of that, or 0.1 amp. So that's the first step. And what I get again is an AC signal, but instead of having its value be 120 volts RMS, it's now going to be 24 volts RMS. The next stage is the rectifier, and in this case we have a diode bridge rectifier. And the job of the rectifier, as we previously mentioned, is to convert the voltage to a single polarity. So we're going from an AC voltage to what's known as a pulsating DC voltage. In this case, we have a diode bridge rectifier, or sometimes simply referred to as a bridge rectifier. And notice that during the positive half cycle, the current is going to flow through the rectifier, and it's going to flow through diode D1. Diode D1 is going to be coupled to the output, and then the output is going to be connected to ground. There's going to be a connection from the load to ground, and so that's going to be coupled to this end of the rectifier right here, and so then the current will flow through D2 and back where it came from, back to the supply. And so the current will go through two diodes during the positive half cycle, D1 and D2, and through the load. During the negative half cycle, current is coming from the bottom end, and therefore it's going to be coupled, coming from down there, going through this D3, which is going to be coupled to the load. Again, that's going to be coupled through to ground, and so through that to diode D4, it's going to flow through diode D4 and then come back to the supply. And so in both cases, the current that's flowing through the load, as we have previously seen, is going to be flowing in the same direction, and therefore we are always going to have a voltage of the same polarity, whether we are in the positive half cycle or the negative half cycle. And we're always going to be going through two diodes, and so we're going to be having two diode drops with respect to the output out of the secondary side of the transformer, two diode drops from that to the output of the rectifier. And so essentially, the value of the rectifier output is going to be approximately equal to V I don't want to call it V in because V in, I'm assuming, is the original AC waveform. So I'm going to go ahead and just put little numbers so that I know out of my transformer, I'm going to say that's point number 1. So this will be my V1. This is going to be out of the rectifier point number 2, point number 3, and point number 4. And I will refer to the voltage values V1, V2, V3, V4 at the different stages in the process. So this is going to be V1, which is the output of the transformer, minus 2 diode drops, which is approximately 1.4 volts. And this is just an approximation. The actual output voltage from the rectifier will likely be a little smaller than that because there are always some losses in the transformer, but also because if we have a large current flowing through those diodes, chances are we're going to have a slightly larger voltage drop. If you remember, there was an exponential relationship between the current and the voltage for a diode, and even though once the diode turns on, the voltage drop remains at approximately 0.7 volts, it slightly increases as the current increases. Let's imagine this a good approximation. And so in our example before, let's say that we had a 24 volt signal, and so our V output in that case is going to be equal to our 24 volts minus 1.4 volts. And that's going to be equal to around 22.6. So that's our signal out of the rectifier. The next step in the process is to run that pulsating DC waveform through a filter. And the job of that filter is going to be that of smoothing that pulsating DC signal, that rectified signal. And so in goes the full wave rectified signal. And what's going to happen is, let's imagine a simple filter. The simplest filter that we can think of is that of a single capacitor. And so as the input waveform or the rectified waveform goes up, then the capacitor starts charging. And so the output of the waveform will also increase. And then as the input signal starts going down, the capacitor, the idea is that it will be large enough that it will hold that final value. It's like a peak detector. In all reality, it's going to always be able to discharge through, mainly through the load. And so it's going to lose part of its value until the next positive input signal comes around, and once it reaches a value that is higher than whatever the value that remains stored in the capacitor is, then it's going to recharge the capacitor back up to the peak value, and so forth. And so what we're going to get out of that process is still this is signal, but with some ripple. Still we can see some pulses in there. And so the ripple is basically the difference between the maximum voltage of that output signal and the minimum voltage that it reaches in between the different cycles. That will give us the amount of ripple, what I've labeled there as V sub ripple. Things that we need to keep in mind is that the capacitor does need to charge, and so we just need to keep in mind that that's going to impose a limit on the type of on the frequency that we need, because it needs to be sufficient time for the capacitor to charge. And since the frequency is something that we typically cannot alter, it's whatever is coming from the AC outlet, we're just going to have to play with the capacitor value, as well as keep in mind the amount of current that we have available to make sure that the capacitor has sufficient time to charge to the final value. Another thing that we need to keep in mind is that the capacitor is going to be discharging, and so we want to maybe be able to calculate how much ripple to expect for a given value of capacitor, and perhaps select a value of capacitor for a maximum value of ripple that we would like to get, or that we would not like to exceed. And so we can see that the equation for the capacitor is that I equals C dV dt. And so, and again, that's imagining that my filter is basically just a capacitor to ground. So this is my V in, which is coming from the rectifier, so that will be V2 in the figure above, and my V out is on the output of the capacitor, and it will be the V3 above, or signal at 0.3 above. So again, I have I equals C dV dt. If I have chosen my capacitor right, sufficiently large, I shouldn't see a lot of discharge in between those two cycles. And so even though there is a decaying exponential relationship for a discharging capacitor, if I'm talking just about a small portion at the very beginning of that exponential decay, I can approximate that discharge, I can approximate it as linear. And it is an approximation, but what I'm essentially saying is that this is approximately equal to, or I won't rewrite the I again, C delta V delta T. So just doing a linear approximation here. Now my capacitor is mostly going to be discharging through whatever load resistance is connected to it, combination of loads and parasitics. So I'm going to refer to that as my I load. And so basically my delta V, which is going to be equal to my ripple, will be equal to my load current divided by C times delta T. And my delta T is the time that my capacitor has to discharge, goes basically from the peak of one pulsating signal to the next. So this is, we could call this my period for my pulsating DC signal. And so I could rewrite this as IL times the period divided by my capacitance. And my period is going to be equal to 1 over F. So I can also express this as IL divided by F times C. Now notice that this is the frequency, F is the frequency of the pulsating DC signal, which you can see is double the frequency of the original AC signal. And therefore, if I wanted to do the calculations for my example above, I wanted to figure out my amount of ripple that I will have, you know, with, if my capacitor was equal to, let's say, 1,000 microfarads, 1 millifarad, then I will have that my ripple voltage will be equal to IL, and we established earlier that my current was 0.5 amps, so this will be 0.5 divided by, and now this is the frequency again of my pulsating DC signal, so it will be twice that of my original AC signal, so 2 times 60, or 120, times 1000 micro. And this comes out to be 4.2 volts, or about 20% of my original signal, my 22.6 volt signal. So notice that there is a substantial amount of ripple still. And it's not uncommon to see a significant amount of ripple for modern power supplies out of the filter, because we have the step of the regulator following it, and the regulator can take care of generating at a stable output voltage. In earlier version or less modern versions of power supplies before the use of regulators, then we might have seen a more complex filter as opposed to just simply a single capacitor filter in order to achieve better performance out of that filter. But like I said, since we have the regulator signal, we're going to see that the regulator is going to take care of finally stabilizing and setting the final DC value to be a constant value. And finally, the last stage in the process is going to be that of the voltage regulator. And the voltage regulator, its job is to provide a stable DC voltage, which is independent or robust to changes in the input voltage, or referred to as the line voltage, the input voltage to the regulator, but also independent of loading conditions. And so I've drawn here the regulator block. I've called the input V sub U for unregulated voltage. That's what goes in. And the output is just V out. Now, for most regulators, or virtually all regulators, the output voltage is going to be slightly lower than the unregulated or input voltage. So there is some voltage drop that goes on within the regulator. So that's something that we need to keep in mind as we are designing our power supplies, that we don't bring the voltage down too far in previous stages, because we're going to also need some headroom for our voltage regulator. There are typically two parameters or two figures of merit to measure the performance of a voltage regulator. And again, since it needs to be robust to changes in line voltage or input voltage and changes in load, those will be the amount of line regulation and load regulation that the regulator provides. Line regulation is defined as the changes in output voltage for changes in input voltage, so the ratio of the delta in output voltage, delta V out, to the delta VU, unregulated or input voltage. That will give you the line regulation. The load regulation is given by the ratio of the error or the maximum delta in output voltage, we should say. So V out when there is no load connected to the circuit or under no load conditions, minus V out under full load conditions, meaning when the circuit is drawing maximum amount of current. And that's all divided by its nominal value, V out under no load conditions. And typically it's expressed as a percentage, so that will be multiplied times 100%. And so again, those are two important figures of merit to measure performance of regulators. A regulator is, in essence, a form of voltage source, and therefore, in the design of a regulator, one of the ideal parameters is going to be a very low output resistance, ideally close to zero. Now notice that the ideal values for line regulation and load regulation are also equal to zero. Ideally, in line regulation, we would like that delta V out to be equal to zero. So if the numerator is zero, our ideal value for line regulation is zero. And load regulation will also be zero, because ideally we would like the output voltage to be unchanged between the full load condition and the no load condition. So ideally zero, the lower the better. So this is it. We've covered the operation of a power supply, and now we're going to get into different types of voltage regulators. Thank you.